So, ladies and gentlemen, welcome to this fantastic event we've got. I can't tell you how thrilled I am to be welcoming Brian Cox. This is a man who literally needs no introduction. I'm not going to give him one, but I am just going to say how delighted we are to have you, Brian, and how thrilled NMITE is as a fledgling institution to have someone of your academic eminence and your commitment to the communication of science and technology and all of the excitement of that. So thank you so much. It's a wonderful thing that you've done, and thank you so much for joining us today.
It's an absolute pleasure. Looking forward to it.
So Brian, you very kindly said, I think, that you've got a few slides that it would be nice to show and talk to get us into the discussion. So why don't you put those up and then we'll take it from there.
Yeah. So just to say, it's a great pleasure to be here. So thank you for joining. And I thought what I'd do is just give a 10 or 15 minutes, just a brief summary of a couple of ideas that I've been thinking about, some of the research that I'm working on now, and also to tee up the discussion, some of the links between science, or let's say a scientific way of thinking, and wider society, which are not just my reflections actually, but the reflections of many scientists. And in particular, I'm going to talk a bit about what Robert Oppenheimer and Richard Feynman, who are both very famous scientists who both worked on the Manhattan Project, thought about the way that nature forces us to think and how that might be useful or helpful in wider society. But first, let me, as Jesse said, show you a few slides just to set the scene for some of the physics that I'm thinking about, and also the issues that physics raises. At the moment, I'm working on black holes, and in particular, a question about black holes that you can trace all the way back to Stephen Hawking and collaborators in the 1980s and 1990s, which is a question about basically what happens to stuff that falls into them, and what that very simple question is teaching us about the nature of space and time, and how that relates to cosmology. And I'll start with a bit of cosmology just to set the scene. What is cosmology? It is the study of the large-scale structure of the universe. In fact, actually, I'm not on screen. I'll show you in a minute. Coincidentally, I've got a textbook next to me, which I'll show you in a moment, The Large-Scale Structure of Space-Time by Stephen Hawking and George Ellis, which is one of the first textbooks on those matters. So cosmology is an ambitious subject. It's concerned with the large-scale structure of the universe, which means the origin, evolution, and fate of the universe. And it's worth just reflecting on the fact that it's a tremendous intellectual achievement that we can even begin, or we can dare to ask those questions and dare to try and answer them in some kind of methodical and structured way. The origin of the universe, the age of the universe, how? How do we speak with any confidence about those issues? To set the scale, I like to show this image, which is one of my favorite images in astronomy. And it's not one of the most spectacular in some ways, but it is, I'm sure you'll agree, beautiful. It's an image of the Earth Moon system in a single photograph. So the crescent Earth and the crescent Moon against the blackness of space. I think it demonstrates very clearly that we are very small and very fragile and insignificant in the universal scheme of things, even in this image. It's a remarkable technological achievement, by the way. You might ask, where is the camera? It's out in space. In fact, it's in Martian orbit. So this was an image taken by the Mars Reconnaissance Orbiter spacecraft and its high-resolution camera, which usually looks at the Martian surface, but can also be swung round to look back to its home world. So it's a remarkable achievement. And I think a very humbling image. Carl Sagan, one of my great heroes, used to say that astronomy is a humbling and character-building experience. And I think you see it vividly in this image. The reason I show that is because this is far too small an object to be of any consequence in cosmology. Cosmology is really begins with the way that galaxies form and the way that they move relative to each other in the universe. And just to set the scale of the ambition, if you like, this is a photograph, another beautiful photograph, this time from Hubble, of one of our nearest neighboring galaxies. It's called the Whirlpool. And you can see this, actually. It's about just under 23 million light years away. which makes it a nearest neighbor. And you can see this almost, not quite with the naked eye, but if you've got a very small telescope, virtually any telescope, and you have a dark night in the northern hemisphere and you know where to look, you can see this galaxy, even though it's 23 million light years away. It's got around, 200 billion stars, which is about average for a galaxy, perhaps a little less in this case. And it's about 100,000 light years across. So light traveling at 300,000 kilometers per second would take 100,000 years to journey across this island of stars. And this is in many ways similar to our own Milky Way galaxy. The Milky Way is a bit bigger. And those are the specks in the universe that we want to understand how the distances between them changes, how they formed, and how the universe will evolve, and how they will be carried along by the stretching of space and time, or space-time, as the universe evolves. So that's a galaxy. And then to really hammer home the scale of the challenge in cosmology, I thought I'd show you one last image, which is this one, which is again a Hubble Space Telescope image, very famous. It's called the Hubble Ultra Deep Field image. And it's an image of a piece of sky that's a fraction of the size of a full moon. It's sometimes described as a small coin held 20 meters away or so from you. So you can imagine it's a very small piece of sky. And Hubble took an exposure over thousands and thousands of seconds over many years, actually, of this piece of sky, which is uninteresting in some ways. It's a piece of sky that was deliberately chosen. So there are no bright stars or nearby galaxies in there. And in fact, every point of light you see in this image, except about 3 or 4, is a galaxy. There are over 10,000 galaxies that have been identified in this single image of that small patch of sky. And the most distant are so distant that light has taken over 13 billion years to travel from those galaxies to us. So this is a deep, almost 4-dimensional image of the universe. And when we take images like this and spread them over the entire sky, we understand that there are of order 2 trillion galaxies in the observable universe, which is the part of the universe we can see. And the challenge of cosmology is to try to understand how that came to be and what's going to happen to it in the future, and how it came to be the way that it is. Just to give you the 1-minute version of what we think at the moment is the story of the origin and evolution of the universe, but beautifully illustrated by this image. We know that 13.8 billion years ago, the universe was very hot and very dense, and there were no stars and no galaxies. And the universe was filled essentially with hydrogen and helium gas and nothing else, almost structureless. And we know that because we can see it, number one. How can we see it? Well, if you think about the Whirlpool galaxy that I just showed, that's 23 million light years away, which means that the light took 23 million years to journey from that galaxy to us. So we see that galaxy in a very real sense as it was 23 million years in the past. So you could ask the question, well, is it possible to look far enough out into the universe that we're gathering light that began its journey very close to the origin of the universe? So light that's been traveling for 13.8 billion years. And the answer is yes, we can. And on this image, actually, you see a thing that's labeled afterglow light pattern, 380,000 years after the Big Bang. That's the furthest back in time we can see, but we can see it, and we have a photograph of it. And the photograph, which you can sort of see here in those colors laid out in this image, is a photograph of the universe as it was 13.8 billion years ago, 380,000 years after the Big Bang. And as I said, what you see is that there are no stars. The stars formed around, this is a bit out of date, actually. We think the first stars formed now around 100 million years after the Big Bang. So the key point is that we know that the universe has not always been the way that we see it today. It is not eternal in that sense. So it was possible, even in the 1950s or so, to believe that our universe had been around forever. In fact, Einstein himself had a predisposition towards an eternal, unchanging universe. And it's more natural, I guess, if you think about it. The idea that you dodge the idea of a moment of creation in your scientific view of the world is kind of attractive in a way. The universe has been around forever. We don't need to explain how it began. That does not seem to be the case, or at least it is the case that what we observe is that the universe was very different 13.8 billion years ago. However, what you also see here is a thing called labeled inflation, and something that says quantum fluctuations, a rather nebulous word, before 380,000 years after the Big Bang. The question today in modern cosmology, one of the central questions, is whether that thing that looks like a beginning is indeed the beginning of time or not. Could it be that the universe existed before it became hot and dense and somehow went through a transition, something changed, and our universe as we see it began, but there was space and time before it? Well, certainly, yes, it could. So could it be that the universe doesn't have an origin in time? Yes. Now, all those questions, these deep questions in fundamental physics, really require an understanding of what space and time are. Without that, we're not going to make much progress in thinking about origins or otherwise of the universe. And the frontier of trying to understand what space and time are currently are black holes. Now, this is an image of a black hole. So the first thing is that these exotic things I'm going to describe for a few minutes do exist. They're real things that exist in nature. Here is one. This image was taken about 18 months ago now by a telescope, an array of telescopes called the Event Horizon Array, which is radio telescopes linked together across the Earth. Actually, one of them's in Antarctica, and there are some in North America, some in Northern Europe, across Asia. And when you link telescopes together, you can build effectively a telescope the size of the Earth. And that's the telescope that took this image. This is the black hole in the center of a nearby galaxy called Messier 87. It's a supermassive black hole, and that's an understatement. It is 6 billion times the mass of the sun. Right? Imagine that, 6 billion times the mass of the sun. The scale of this image is, it's not very big. It's about, let's say, 3 solar system diameters across or something. So it's kind of big in some ways, but if you think there's the mass of 6 billion suns in there, then it's pretty small and pretty violent object. And what you're seeing is that dark shadow in the middle, inside which is the so-called event horizon of the black hole. And surrounding it is the glowing gas, star systems and gas that are being ripped apart and spiraling into the black hole, emitting radiation. That's called the accretion disk. And so this image is a remarkable achievement because it's so far away, about 50 million light years away or so. And the predictions of Einstein's theory of general relativity, which was first published in 1915, so over 100 years ago, were verified and have been verified by looking at this image in detail. So it's another example of the power of the human mind. Einstein, by the way, didn't like black holes too much. He felt that they were too absurd to exist, although his theory strongly suggests they do. And just let me give you a sense of what we're beginning to discover and how these things may be allowing us to unlock the deeper structure of space and time. I'll give you one example of that. There are many which we could discuss in the questions, but let me just give you one. So back in the 1980s, as I said, and 90s, Stephen Hawking and others asked the question, what happens to information if it falls into a black hole? You may know that a black hole is often characterized by this thing called the event horizon, which is a giant sphere in space. It's one way to think about it, which is not there in some sense, but it's a barrier in another sense, in that if you cross it, which you could do without feeling any ill effects at all, for this black hole, you could fall across the event horizon into what you might call the interior. Space and time would feel the same to you in there, but you couldn't get out. You would have to travel faster than the speed of light to get out. It's an eternal prison. And more than that, once you're inside the event horizon, it turns out that this, what you might call the center of the black hole, the thing called the singularity, is actually a moment in time. It becomes a moment in your future. And so you can't avoid the end of time once you've crossed the event horizon. I should say that it's, for this black hole, it's something like a couple of hours in your future. So it's not so far in your future, but it's there. You can't dodge it in the same way that you can't dodge going to tomorrow. So you tried running around in your room now and avoiding getting to tomorrow, and you find out that you can't do it. That's what happens to space and time inside a black hole. So the question was, well, what happens to information if you throw it into the black hole, does it get destroyed? Does it go to the end of time? Stephen Hawking showed that black holes evaporate away in a process called Hawking radiation over vast timescales. And so whatever happens to this black hole is not eternal. It will one day have gone. I should say it's something like 10 to the power 100 years in the future. So it's a long time, but in principle, it will have gone. And it will go by emitting so-called Hawking radiation. The question was, is the information that fell into the black hole imprinted in the radiation or not? Or does the black hole destroy information? If it destroys information, that means that determinism in the universe is false. It doesn't work. It's one of the fundamental articles of faith in modern science and physics, that if you know everything about something at some point, then you can predict what it's going to do in the future and what it did in the past. If you've got something that destroys information, you can't know everything. And so you can't predict the future. So it's a very serious fundamental question. Do these things destroy information? The answer seems to be they don't. But let me tell you how that, with only 1 minute, because I'll talk for too long, but in that sentence, we go to the cutting edge of modern research. What we discovered is that essentially, if you ask the question, what happens if I throw one bit of information into this black hole? It turns out the black hole expands, and it expands such that the surface area of its event horizon increases by a fundamental thing called the Planck length. So a tiny little expanse. It's almost as if it's pixelated, but it's the area that expands. And so what that's telling us is that if you store information in the volume of space, then in some sense, the volume of space doesn't matter. It's like saying, how much information can you get in the library? Is it something to do with the volume? Is it to do with how many books I can fit in the library? The answer seems to be no. It's as if nature tells you that you're only allowed to paper the outside of the library with books. That's the maximum amount of information you can get in. In fact, I'll stop my sharing at the moment so I can talk to you like this. So what that's saying is it seems to be saying that space and time are not what they seem. And actually, in some sense, it's only the surface of an area, of a region of space that matters, and not the interior. So there's a suggestion that space and time are built out of smaller things. And those smaller things, we might call them atoms of space and time, are somehow related to the area of a surface. And the volume is somehow not there. It somehow doesn't exist. And that's how we come to these ideas that you might have heard of, that we're all holograms. That's what a hologram is. So I won't go much deeper into that. I'll just say that what's interesting to me and many physicists, and I think just interesting philosophically, is that the study of these real things, black holes that exist in the sky, is forcing us to reassess what we think space and time are, the fundamental nature of reality themselves, which is a very deep insight, I think, into the power of physics and mathematics, which is what's being deployed to think about black holes. Now, I'll leave that for questions if you want. The last thing I want to say, because I don't want to take too much time, is to just pick up that thing I said at the start about that idea that thinking in this way might be useful in other areas of society. So not obviously science is useful. Obviously, it underpins our modern civilization, medical technology, the vaccine rollout that we're seeing at the moment, electronics and so on. It's all based on science, obviously. But the question that many people ask is, but I've just described a strange way of thinking, in a way, an unusual way of thinking, which is I'm going to drill down into this weird thing that we don't understand. I'm going to be delighted in coming face to face with the frightening unknown, which is what black holes represent. And I'm going to try and explore what they mean. And if they mean that space and time are not what they seem, then so be it, we'll go down that road. That's a way of thinking. First of all, it's celebrating not knowing. It's celebrating the fact that there is an edge to our knowledge, not being terrified of the darkness beyond, but walking up to the edge and peering into the distance to try to find out more about nature. And if nature comes back with an answer that we're not expecting, which is it seems that space doesn't exist in this case, and time doesn't exist, that there's something deeper, then so be it. We follow down that road without prejudice or without being offended that our preconceptions are being challenged. Right? Oppenheimer and Feynman, two of my great heroes, both worked on the Manhattan Project, and both, I think, not coincidentally, thought very deeply about these issues in the 1950s after they had delivered the atom bomb to society, to politicians and to us and so on, to use or not use, to use as a deterrent, whatever. Great power was given to our society through the pursuit of knowledge, in this case, the Manhattan Project. And both of them reflected on, first of all, whether that was morally right. Essentially, what they were claiming is that we are not wise enough to control the knowledge that we acquire. That was the very strong sense in the 1950s. You can see why, because this was pre-Cuban Missile Crisis even. So it could well have gone the other way in the 1950s and 60s and 70s and 80s, and could well still go the other way in terms of the possession of nuclear weapons and their use. And so many of the scientists that worked on them thought about that knowledge and what it means, and the problems of having deep knowledge of nature. And I thought I'd just read, to finish, some of Richard Feynman's reflections. What did he think? He wrote a beautiful essay, which I recommend to all of you, that you can get if you go online, type Richard Feynman, The Value of Science, The Value of Science. You can get the PDF, it's freely downloadable. It's a brilliant essay reflecting on these issues I'm sure we'll talk about in the Q&A. And Feynman said, the most valuable thing of all about the study of nature, and the reason I would say that we should all do some experimental science at some point through our careers, because you taught this very important, it's very viscerally, I would say. The most important thing is that you get a great experience with being wrong. Now, it's obvious in what I said about black holes. If you walk to the edge of knowledge, then you are going to be wrong when you speculate more than you're going to be right. And nature forces you into being wrong most of the time when you choose to explore it. And Feynman said that's tremendously valuable. He called science actually a satisfactory philosophy of ignorance. And I thought I'd read you the end. It's worth reading the whole essay. But this is the last paragraph or so of Feynman's essay, in which he reflects on what that means. What does it teach us? What does the experience of being wrong teach us about the way we should behave as a society and as citizens and as governments and politicians and so on? What does it teach us? Well, here's what Feynman said. He said, it's not unreasonable that we grapple with problems, but there are tens of thousands of years in the future. Our responsibility is to do what we can, learn what we can, improve the solutions and pass them on. But it's our responsibility to leave the people of the future a free hand. In the impetuous youth of humanity, we make grave errors that can stunt our growth for a long time. This we will do if we say we have the answers now, so young and ignorant as we are. If we suppress all discussion, all criticism, proclaiming this is the answer, my friends, man is saved, we will doom humanity for a long time to the chains of authority, confined to the limits of our present imagination. It's been done so many times before. It is our responsibility as scientists, knowing the great progress which comes from a satisfactory philosophy of ignorance, the great progress which is the fruit of freedom of thought, to proclaim the value of this freedom, to teach how doubt is not to be feared but welcomed and discussed, and to demand this freedom as our duty to all coming generations. Isn't that powerful? And that, I think, is the best example I know of what studying nature honestly and with an open mind can deliver as a transferable skill. And what we should aim to do is transfer that skill to as many people as possible.
Well, Brian, I mean, how to react to such a tour de force. Thank you so much. I must say that I can't imagine a better way to, as it were, anchor our summer of discovery at NMITE than to have a conversation about as it were, the limits of technology, the limits of science, and the obligations they place on individuals in whatever, as practitioners or in other places of authority. And there does seem to be something about that moment, the Feynman-Oppenheimer moment that you describe, where people had, I suppose, two or three things. One is you were dealing with geniuses who didn't just have a particularly blinkered professional understanding of what they were doing. They looked at the horizon. There seemed to be a kind of wide-scale moral awareness, and of course, this was, I guess, in the Cold War or leading into it, and therefore, you know, the question of whether everyone was on the same side on nuclear weapons was a live question, and whether there were politics associated with that. There certainly was in America. And the other thing, in a way more deeply, perhaps, is this idea of the fallible, of doubt, that, as you say, we should embrace it. And I can't help thinking that there are lots of places, and indeed COVID today is one of those examples where, you know, an awareness, an openness to the possibility that one might be wrong, and a more provisional way of thinking would be terribly helpful.
Yeah, you think about the pandemic and the tremendous pace of innovation, certainly surrounding vaccines. It's worth reflecting that 18 months ago or so, this virus was unknown completely, and may well not have been in humans if you go back 18 months or 2 years, right? So it just wasn't known. And you go from knowing nothing about something to understanding its genetics, and to building vaccines, some of which were based on previous technologies, some of which are new technologies, and deploying them successfully in a period of 18 months. It's astonishing. But implicit in that is the fact that we went from knowing nothing at all to knowing something. And so the idea that you can look back at the way we responded with advice, you know, but the advice about, let's say, mask wearing or social distancing or all that stuff. Obviously, we learned more about the virus because we know something about it now when we knew nothing about it 18 months ago. So you can't argue that we've learned. What Feynman has said, and I haven't really mentioned Oppenheimer, I'll talk about him in a moment. What they said is that the recognition that is the way that we progress. It's obvious to say, but by recognizing that and being open about it, and by saying, I've now changed my mind, we did something that was not optimal. How is it going to be optimal? Because we don't know, we don't have absolute knowledge. So we're never going to make optimal decisions about these things. But the idea that you set up a society, which I think we all recognize that we are in to some extent, where, for example, maybe you can comment on this, Jesse, but where, for example, politicians feel that they are unable or unwilling to change course when new evidence or new data comes in, because it makes them look weak in somehow. When actually what Feynman said beautifully and eloquently there is, it's not weakness, it's strength. It's the foundation on which progress is built. But if you never say, I was wrong, there will be no progress. And how we, I think it's not only politicians have a responsibility. And I'd love to know what you think, Jesse, but I think it's also the public, because we've got to stop lambasting people when they say, well, actually, no, I've changed my mind now because I've learned something.
Yes. I think there's a great deal of truth in that. The trouble is that scientists, when they change their mind, often do so because a community of thought has reached its kind of intellectual limit, and someone has got to, as it were, call out, and then the paradigm shift occurs. And in politics, the complexity of the thing and the pace of change means that if you change your mind every few weeks with the change in the evidence, very soon you're going to get called out. So there's a balance to be struck. What I think is so interesting, though, about the era that you mentioned is that you did have a kind of what seems like a more morally engaged discussion, perhaps, than existed in the 20 or 30 years that followed that. But also there was something slightly heroic about the individual scientists. I mean, these people happen to know they were moving the dial, but for 99% of all scientists, they don't know they're moving the dial. They're engaged in a massive collective endeavor. And they don't necessarily expect to have their names all over the front pages, and they're doing something in more or less the certainty that no one will ever recognize it except a very small number of their peers, and that does give it a rather heroic character.
Yeah. I mean, Oppenheimer, I should say, in the 30s, before the Manhattan Project, he was one of the he did a lot of work on black holes, actually, for which he's kind of well known scientifically, but the Manhattan Project dominated his thinking. I should say that Oppenheimer, again, if you're looking for things to read, so that Feynman essay, The Value of Science, 1955, I think it is. In 53, Oppenheimer gave the BBC Reith Lectures, which are also available freely online. And they're remarkable things. That it was considered a failure, actually, at the time, because it was very dense and he didn't mention the atom bomb. So it's like Queen not playing Bohemian Rhapsody, right? In a way, he didn't do his greatest hits. But he talks about science and society. And there's one thing that there's so many things. It's a wonderful piece. It shows the genius of Oppenheimer. It's wonderful to read. Science in the Common Understanding, it's called. And then, again, he's concerned with this, what's the transferable skill? And one thing that always struck with me, he said, he talks about, by analogy, with quantum mechanics. So quantum mechanics is famously arcane and unusual. So, for example, if you think of a particle like an electron, right, and a particle of electricity, I suppose our picture, when I say particle, is a little point-like thing like a grain of sand that bounces around like a game of billiards. And but it's not like that. It's sometimes appropriate to think of an electron like that, but it's also appropriate to think of it as some kind of extended wavy type thing that fills any container in which you try to confine it. And actually, the truth is neither. The truth is that it's some combination of those things. And so we're choosing different ways of looking at the world, different ways of looking at the electron, some of which are appropriate sometimes, some of which aren't. So it's a complicated thing, but you have to, and this is the key point, you have to hold both of those ideas and some more in your head at the same time in order to get a complete picture. And Oppenheimer said, so it is with society. So in society, there are different political positions. There are different tensions. So there's the requirement that we respect the rights of the individual, and also that we understand that we live in a collective. There is such a thing as society. And what we tend to do is we tend to identify with one or the other of those ways of thought or the political tradition associated with it. And so we say, in Oppenheimer's language, he would have said, so we might be a communist, which is weighting towards society, or we might be a libertarian, which is weighting towards the individual, and so on. What nature tells us, and it goes back to what you just said, Jesse, about the complication of society. What we learn is that all those things are necessary points of view. Right? There are no rights and wrongs here. There's a spectrum. It's so complicated that you have to hold all those things in your head at the same time. And what will happen is the weighting you give to the different ideas will change as you change your, as you grow up, as you change, as your circumstances change, as the circumstances of society changes, the weighting will change. And so you can't say, I am this, I am a communist, or I am a conservative, or I am a whatever it is. What you're doing there is narrowing down the scope of your description and understanding of society. And he even went further, which I thought was very beautiful. He said, and it's very topical at the moment, actually, what happens when someone disagrees with you or you disagree with them in politics, for example? What happens if you don't like the government at the time, you don't like this or that? How are you supposed to react? What Oppenheimer pointed out is that if you live in what does it mean to live in a free society, which Feynman also referred to in that essay of freedom? What does it mean? It means that you will disagree with others and others will disagree with you, because the opposite, if everyone agreed with everyone, I think that would be a very strong signal that you didn't live in a free society, right? It's not going to happen. But if that's what it looks like, then you're not free. And so what you put them together, and Feynman's idea about changing your mind, and what you get is sort of a picture of a pendulum that swings between. So sometimes things will go your way, sometimes they won't. Sometimes a country will go in one direction, sometimes another direction, and so on. The weightings between individual freedom and society will change over time and swing. As Feynman pointed out, that's a signal that you live in a free society. That's what democracy is. Democracy is the acceptance that you don't know what you're doing, because it's the acceptance that you change things every 4 or 5 years. If you knew what you were doing, you wouldn't change things every 4 or 5 years. And so the swing of the pendulum towards you and away from you is an illustration or a manifestation of the fact that you live in a free society. And it's also the guarantor of your freedom, because the moment that pendulum stops swinging, you are no longer free. And that's what Oppenheimer and Feynman explored in great depth, and I think with great wisdom. And I think we've forgotten a lot of it.
How absolutely fabulous. Well, we're going to bolt those into the curriculum at NMITE for all arriving, Brian, just for those reasons. It's very interesting what you said. Let me pick up a couple of little things. So one way of characterizing what you said about I am a this or I am a that, is that it places a kind of break or a rest on what is essentially a continuous or evolving activity. And science itself is par excellence a continuous and evolving activity. As soon as you impose some kind of arrest, you're doing a kind of logical violence to what's really the underlying activity. I always think that the right metaphor for society is a more chemical one. You know, we have individuals with bonds between themselves and they form molecules or associations, and then those associations might form relationships of chemical valence, whatever it might be, between themselves. And over time, you can never predict what emerges, but there will be supervenient properties to the whole which characterize what the society actually is. So you can get different societies with different characteristics, and it can be simultaneously true, taking your two viewpoints, that as it were, there are only individuals and the valences and bonds between them and the molecular relationships that build up. But also there's something very powerful and important called the whole, which everyone is seeking to preserve and enhance and develop. And the same would be true for smaller institutions like institutions of science as they would be for society as a whole.
Yeah, absolutely.
That is, let me just, I mean, I'm very keen to encourage a lot more questions. We've got lots of people waiting. We've got a few questions, I'm pleased to say, lining up. Ladies and gentlemen, if you want to feed in some questions, please shoot them into the Q&A so that when we turn over to you in a couple of minutes, we'll be ready to fire those into Brian. Before we do that, Brian, I can't help asking, if you could just spend a second telling us, this is an NMITE thing, how on earth you got it into physics, how you got into cosmology. I mean, you've dazzled us with the scale and the fascination of what you've been talking about, but you know, you've also been on top of the pops. That's an interesting
Yeah, I mean, I think the key thing is I didn't know really what I wanted to do when I was, 16, 17, 18. I did, in a way, I'd always been interested in astronomy from way back. I had some binoculars. I used to go out and look at the sky. I come from Oldham, and one of the great things about Oldham is that we have the Yorkshire moors, and you can go up onto the moors and it's very dark and you can see the sky. And that's what I used to do. So I'd always had an idea that I would love to be an astronomer, but I was told it was impossible, actually. I mean, the careers people at my school could not comprehend that you could be a professional astronomer. So actually they kind of, I was better at the sciences. So they guided me towards engineering, which is a wonderful thing to do. And I thought about that. But then I also was interested in music. I actually got interested in a geeky way. I was into electronic music, and I quite liked the sort of the hardware of it at the time. And so I'd been in local bands.
And to do with a synthesizer.
Yeah, exactly. So I've been in local bands, and I got the opportunity to join a band that got a record deal. And so when I was about to do my A-levels and go to university, I was already in this band, this local band that was doing well. And we got a record deal. So I took a year off from going to university. And then that deal blossomed, and we made 2 albums and toured with my first professional gig actually was supporting Jimmy Page, if those of you are old enough to remember Led Zeppelin. So I had some wonderful shows. And so I did that for 5 years, and then left that band when I was 23 and applied to Manchester University to do physics. Got in, accidentally joined another band when I was an undergraduate, which was the band D Ream, which you probably have heard of. And we had the song things can only get better, which turned out to be incorrect. Which Tony Blair used in '97. And so I kind of bounced around between a couple of careers. And I think that's reflected. It's always been a part of my character. I suppose everyone who's watching this, many of you might not really know what you want to do. You might be interested in music and literature as well as sciences and the arts. And I think it's important to know that the important thing is that you're curious and to know that you can change course. I mean, I've changed course several times. I've made some TV programs as well. I never thought I'd do that. So I've changed course several times. I think the key thing is to be interested in the world. And just one last thing, which occurs to me, which there's a wonderful book. If I'm recommending books, I've recommended 2 things already. Let me recommend another one called Godel, Escher and Bach by Douglas Hofstadter, very famous book. Godel is the mathematician and Escher the artist and Bach the musician. And what he argues, and I think it's very true, is that you think about what we're trying to learn. What are we doing? What is this thing? What does it mean to be human? Right? There's some central thing there that we're trying to explore through our endeavors. Science, music, art, philosophy, theology, all those things. What they do is they shine lights on this central thing. What does it mean to be human? What's the meaning of it all? Right? And they cast shadows. And we have access to the shadows. We don't have access to the real thing, but the more lights we can shine on it, the more shadows we can see, and the more likely we are to get a deeper understanding of what it means to be human, and therefore to live full and productive lives. So I think that's a very important thing. I don't think any of us are scientists or artists or musicians. I think we're all go back to Oppenheimer, a combination of all of them. And it's worthwhile embracing that rather than rather than being railroaded. Don't let yourself be railroaded. That would be my thing. Take that whole landscape of human ideas and possibilities seriously, and you will have a good time.
How absolutely fabulous. So we're not blinking from Plato's cave into the sunlight. We're really looking at a kind of X-ray crystallography, a diffraction of different parts of human life and different.
That's a very good analogy, and I think that's really true. Just to say very briefly, I collaborated recently with a couple of orchestras. And so the cosmology that I just described a sprinkling of it, 2 trillion galaxies in the observable universe. What does it mean? Ultimately, it comes down to a question, which I think is the only interesting philosophical question. And then Jesse and everyone else can disagree with me. I'll be bold, right? The only interesting philosophical question is, what does it mean to live a small, finite life in an infinite, eternal universe? That's it. There is no other question that interests me, right? And cosmology brings you face to face with that. We're tiny, physically insignificant in this vast universe. What does it mean? Well, if you look at some of the great musicians of the past, so Mahler in particular, I'm a great fan of Mahler. Mahler was very interested in what it means to live a finite life. Although he didn't really like to interpret his own music, it was certainly underpinned a lot of his work, was the idea of death and what it means to be small and fragile and finite. He answers that question powerfully, particularly for me in the first movement of his 10th symphony, but there are many other stuff. He approaches and delivers answers to that question. Those are questions raised by cosmology. So science, the study of nature, brings us face to face with existential questions, but don't expect science to answer them, because, as I said, you need to shine all the lights on these complex ideas. And so, it just popped into my mind that's.
How pretty gorgeous. Well, what you've got Mahler, I've got Miles Davis, but I think we're in the same.
Miles Davis, I'm with you. Actually, I just say, if you like me, I was been introduced to new things. I've got one of those, those algorithms on my music thing that just says, why don't you listen to this? Why don't you listen to that? And it introduced me to a performance of Somewhere Over the Rainbow, the very famous song by Keith Jarrett. So if you know Miles Davis, you'll know Keith Jarrett. He did a very famous recording called La Scala, which is mainly ad-libbed, but at the end he played Somewhere Over the Rainbow. And it's the most beautiful rendition of that song. And I was talking to a friend of mine about it, and he said it's almost like he's a musical archaeologist, because he found something in that song that wasn't there. I don't know how he mined the harmony and melody to bring out the things that he did. But yeah, again, always discovering new things.
There was so many.
Jarrett, that's another one I recommend.
I'm not saying anything. We're going to take the first question from Christo, who's of course, I'm pleased to say, paid you the ultimate compliment of asking you a question about information and black holes. Brian. So Christo asks, have we tried to decipher the information contained that you get from the radiation that black holes emit? Does that bear on the information paradox that you're describing?
An incredibly good question. So the first thing is we haven't detected Hawking radiation. It's impossible to detect in any conceivable future. It's tiny. The black holes at the moment are so freezing cold that they're not actually radiating. They're absorbing energy from the universe. So we're talking about, a theoretical process that we are never likely ever to observe. However, using the basic principles of physics as we understand them, we can interrogate that question that you asked. And very recently, the end of 2019, a series of papers were published that purport, and I think are widely accepted, to describe how the information is encoded in the Hawking radiation. And it's one of the most stunning results in theoretical physics, because it seems that the information is encoded in the same way that we have to encode the information in the memory of quantum computers, which are technologies that we build today, in order to prevent errors from creeping into the quantum computer, so-called quantum error correction code. Now, that is a mind-blowing discovery, because it's linking very deeply fundamental issues in information processing that we confront when we attempt to build quantum computers, which is what we're doing at the moment, and ultimately the structure of space and time. So there's a link, and the idea that somehow the information coding in the universe appears to be redundant, right, is astonishing. Let me just say that is not to suggest that we live in a computer simulation before anybody asks. I think that's going too far. I did say once that if the 20th century taught us that God was a mathematician, the 21st century is teaching us that God is a programmer, right? But it may well be what we find. A quantum computer is basically a natural object, right? Quantum computers they're using the laws that underpin the way the universe works in order to function. And so it may just be a case of nature solving a problem that we are attempting to solve. There may be a way to solve the problem of entangling bits of quantum information so you get some robust system. That seems to be the modern view of what the universe is. It's an information theoretic description. So yeah, it's a very good question. And the answer to it is leading us deeper into this link between the building blocks of space and time and quantum mechanics and how it's all entangled together, and how the world that we inhabit emerges from that deeper structure.
I mean, it is kind of mind-boggling to think that a black hole has evolved in a way that, as it were, encodes this quantum theoretic view of the world informationally in the same way that we're kind of discovering here, and that therefore perhaps from a mathematical description standpoint, they're the same thing, or one is a natural object as much as the other.
It's called the dual theory, and it's actually not just the black hole; it's space and time. So what you're really talking about is the structure of space-time, the underlying structure. It becomes, black holes are interesting. They're like Rosetta Stones because they're where the problems emerge in our understanding. So they force you into investigating the structure of space and time more carefully because of the problems they pose. Yes,
how fantastic. Now, we've had another quick question on black holes, which is about white holes, and it's something I know nothing about. He said there's also another theory from an anonymous attendee about white holes, that objects get pulled in by black holes and then spat out by white holes. Do you believe in that theory? Is there currency to that, do you think?
That occurs when you have a black hole that's eternal. So the thing about black holes, the description of them in Einstein's theory is called the so-called Schwarzschild metric, which is a remarkable thing, by the way. Carl Schwarzschild discovered this solution to Einstein's equations about a month after Einstein published the theory in 1915, whilst he was on the Russian front. Right, he was an artillery in the German Imperial Army, as it was, on the Russian front in the First World War, 1915, and solved the equations whilst he was involved in that. So it's quite remarkable. So the Schwarzschild solution is it describes a space-time, a geometry of space and time, which you can consider as being eternal and unchanging. And it's an idealization. And in those geometries, you have these things of the other side of a black hole, if you like, the white hole bits. And you can, but the thing is that those geometries are formed in nature by something happening, by a star collapsing. So black holes are not there; they're a big star, and then they form into a black hole when the star runs out of fuel. So they're not eternal. So those geometries are allowed in the textbooks, but we don't think they occur in nature.
How interesting. And it's so often the case that a mathematical idea is kind of conceived and put in a little box and then turns out to be useful in the future.
It's incredible. I mean, I should say, so the Schwarzschild solution, this remarkable thing in 1915, which Einstein immediately recognized as a work of genius, it describes how planets orbit around the sun, for example. And the reason, it also describes black holes. It predicts them. But what Oppenheimer and many people spent all their time in the 20s and 30s trying to do was to show that black holes wouldn't form in nature because the consequences are so absurd, which was Arthur Eddington, a very famous physicist, word, absurd. Such absurd things shouldn't form. And so whilst the theory allows them, the reason is, I'll just give you the very brief reason. This beautiful geometry of space and time around a star, which is what Schwarzschild thought he'd worked out, is all fine. But it's not applicable inside the star. So you can go to the surface of the sun and it describes how space and time are curved and warped, and therefore how planets would move across that surface. And it's all very beautiful. And you just stop at the surface of the star. But you could ask the question, what happens if you squash the star down and carry on squashing it until you basically squash it down to a point? What does the geometry look like? And it turns out that if you squash the sun below 3 kilometers, right, so down into a ball less than about 3 kilometers, then you reveal some space around it where you get this thing called the event horizon, and you can think of it as being, if you squash the sun down into a ball, let's say you squashed it into about a marble sized thing, right, and it could stop somehow, then if you stood on the surface, you'd have to travel faster than the speed of light to get off. The escape velocity is too high, right? And that's one kind of way of thinking about it. So what people thought, though, was that you can't squash a star into something the size of a marble, so it's all fine, it doesn't matter. But it turns out you can. And they do. They collapse almost basically out of existence. And so you reveal this part of the geometry, which is weird, pathological, odd. And that's what a black hole is. Yeah. But that's why Einstein didn't think that the star would collapse.
So some things can go from being absurd to being conventional wisdom in a generation, or even possibly less than that.
I can think of I can think of so many jokes about politics where that's happened, but I'm not going to make them.
Let's not go there. We've got Rowena, who's asked a question. Look, you've been talking about incredibly interestingly about this diversity of ideas, and do you think that means a need for greater diversity of thinkers in the research community? And one might think of gender, ethnic, neuro, etc. And is that a precondition for future breakthroughs? Should we only be, as it were, privileging cognitive diversity? That is, as it were, lots of miserable sods saying, "I don't agree with that. What about this?" I mean, how do you think about that?
So yes, you're absolutely right. Trying to understand nature is hard. And it's, again, maybe the analogy about shining the lights works in this case as well. The more lights you can shine on the problem, the more likely you are to solve the problem. And so I agree absolutely. I don't think it's not a prerequisite in that very strong sense. I think I'm probably going too far, but it is an extremely desirable and will help, because again it's obvious in a way, but Einstein is a good example. I mean, he really did think in pictures, and it was an unusual way of thinking. And that way of thinking turned out to be extremely fruitful. And you see it over and over again. So, yeah, I think the more diversity of thought and background and approach you have to this difficult problem, and when I put it like that, it's almost self-evident, the more likely we are to solve the problem.
I mean, one of the things that's really interesting, sitting in the back of something you said, Brian, just to develop that a bit, is the question of what the ego should be of the scientist, because you want enough ego to be really believing in one's ideas and pressing forward with research and powering that. But you want also enough restraints on ego to be open to the possibility of change and to be able to collaborate, almost a kind of Buddhist view. Do you have any thoughts about that? One of the things we're thinking about with NMITE is how we build in open-mindedness, as well as how you build in teamwork and gender diversity, because of a kind of view that actually you will get better outcomes if you do both of those things.
Yeah, I think it's I think about this quite a lot. I think it's the difference in your mind between wanting to know and wanting to be right. And there's a really fundamental difference, because if you just want to know, which means you want to understand, which is just the way that I think, right? I just want to, there's a great joy, which all of us who've grappled with a difficult problem and suddenly seen a solution or come to an understanding will recognize it. There's a great joy in understanding. And the way you understand, if you think about it and you're honest with yourself, is to keep going and going, I don't understand, I'm not right, this isn't right, and keep going. It's one of the most fundamental skills in education, actually, that you don't kid yourself, that you're honest and you just keep going. I don't understand, and you keep going until you understand it. So if that's the way you approach a problem and approach life, then you are not going to care about being wrong. There is no, you don't need, it doesn't, because it's such a fundamental part of your process in, I suppose, in the joyful process of understanding, that you genuinely, as Feynman said, he wasn't joking when he said, doubt is not to be feared but welcomed. Right? That I think it's natural to someone who wants to know and understand rather than wants to be seen to be right.
That is such a good way of thinking of it. And also, of course, Feynman was such a joyful person, a constant capacity to take exciting aspects of the world and make something more of them. Yeah. So, ladies and gentlemen, we're a couple of minutes before the hour. We're going to we might run another 5 or 10 minutes on, so we've got plenty of time to get questions in. I've got a couple of quick fire questions here, Brian. We've got one writer who said, I am just for a question. The question was, I'm a research scientist from China. How may I join your team? And I don't know if the answer would be send me your CV at University of Manchester, or, but I just, it's worth mentioning.
Yeah, and I should say there are a lot of people working on the black hole information paradox across the world. And also in China, of course, you have some of the most powerful radio telescopes in the world. I mean, the biggest actually at the moment. And so I think that there is the University of Manchester, where of course you can keep an eye on the postdoc places and things that we have. But I would say that this is a very widely spaced effort around the world, because it's so interesting and because it overlaps in the most bizarre way that no one could have imagined. Quantum computing is one of the most well-funded and research fields now, right? It's a good lesson here, actually, because governments are everywhere are throwing money into quantum computing because it's so potentially powerful. It's a tremendous breakthrough technology. What's really interesting is that one of the most profound challenges in quantum computing, which is error correction, very basic challenge, it turns out that it's intimately linked to questions about black holes and space-time. And so there's serendipity. And this is why it's so difficult for governments and funding agencies to, not even so difficult, it's why they shouldn't try too hard to somehow fund science optimally, because that's not possible. Because no one would have thought that funding some people thinking about black holes would have led to deep insights into how to build the memory of quantum computers and the algorithms that we use. But that seems to be the case. So I've been on funding bodies, and it's a very difficult challenge. But ultimately, recognizing that there's a place for serendipity is extremely important.
Yeah, well, I couldn't agree with you more. And also, there's something about the official and indeed the political mindset. And listen, I'm a Treasury Minister. Everyone panics about value for money. But the idea that that can push you into an optimal funding arrangement, as you say, is actually
it's not right.
doomed to failure. I always think there'll be more, and we touched on this earlier, but I always think that one of the areas in government where we are weakest is in error correction. Just asking a question, did the policy work? If so, how far, under what circumstances? You can go back and look at it. I once suggested that the proceedings of the Monetary Policy Committee should be published, the intimate discussion should be published 5 years after the event. So people just check whether the Monetary Policy Committee had actually got it right or were thinking about it. No one liked that idea. That was extreme. The bank,
yeah, I suppose it's just in that sentence.
True elsewhere, I think.
I think it's just in that sentence. It got it right is probably the issue. The point is that there's no right and wrong, is there? In that you're making decisions about complex systems with limited data. But the point is that the whole goal of it should be to make better decisions in future, not to try and assess who got what wrong in the past. If you flip it round, it becomes natural that you'll try and measure, in some sense, how well you did, not because that's part of your promotion, or whether you get made knighted or something like that if you got it right, but just so that we can make better decisions in the future.
Yes, of course. The difficulty, I mean, this is supposed to be a quick question, so we're spending a bit of time on it, but there's a kind of blagocracy problem, right? That actually what we're rewarding is people who can blag their way through things, rather than people who actually have a record of giving effective advice, and institutions that have a record. So you're right, they'll never be optimal in a sense, but we can still differentiate better between good and bad, and we should do.
Yeah, I suppose we talked about transferable skills earlier when you study science, and why experimental science in schools is really important. And that's just because you're not allowed to have an opinion about gravity, for example. If you drop a ball, what happens? You can actually do that experiment. And no matter how well trained you are at debating or whatever, ultimately you can drop the ball to find out.
Quite. Second silly question. Please, can Professor Cox explain his T-shirt at this time?
Oh, it's actually, so this equation is, I showed that picture of the universe expanding, the stretching universe. It's called the Friedman Equation. And it's the thing that comes out of Einstein's theory. I should say, one of the wonderful things about Einstein's theory of gravity is it's a theory of space and time, right? It's this fabric of the universe. And his picture of gravity is you put something like the sun in the fabric of the universe and it distorts it. And that means that if you send things around close to the sun, that they won't go in a straight line. They'll deviate. And that's it. That's what gravity is. But it also, and Einstein, this is a great example of what we've been talking about, actually. Einstein in 1917 said, I'm about to now try something that may see me consigned to a madhouse, right? And his idea was this. He thought, well, if you put a star in the fabric of the universe and it distorts it, then, and so we can calculate how planets orbit around stars, then what happens if I apply that to the entire universe? What does the universe do? If I sprinkle galaxies through the universe, what does the fabric do? So it distorts close to the galaxies, but does it do anything else? Turns out, yeah, it does. It tends to stretch, right? And so, and in fact, Einstein in 1917, 1918, 19 noticed that whatever he did and whatever kind of matter distribution he tended to assume and throw into his equations, there's a tendency for the fabric to stretch. And that's telling you that if you go back in time, there's a tendency for it to shrink. And so everything gets closer together as you run time backwards. And Einstein didn't like that at all. He thought because he wanted the universe to be eternal. So he tried to fiddle around with the equations and introduced a new thing called the cosmological constant, all sorts of stuff, to try and balance the tendency for the fabric to change. And there's another great mathematician who's also a priest, a Belgian priest called Georges Lemaitre. And Lemaitre did the same thing at the same time, got the same answer. But perhaps, I'm sure, actually, partly because he was a priest, if you see that you've got a theory that's suggesting that distances between things get shorter as you go backwards in time, it's suggesting quite strongly there's a beginning, right? A moment of creation. And he wrote to Einstein and said, your theory suggests there was a day without a yesterday. And Einstein wrote back to him and said, your mathematics is excellent, but your physical intuition is lousy. So Einstein was wrong and ultimately accepted it. Einstein, to an extent, ignored what his theory was screaming at him, which is that it looks like there's a Big Bang. And Lemaitre saw it.
How fabulous. Well, Laura, I bet you didn't know you were going to get an answer of that quality.
No, that's the equation that describes that. So it basically, it says, put something in the universe, what does it do? And this picture is, if you put a lot of stuff in the universe, it's closed, which means it recollapses to a big crunch, which is not what we think the universe is like.
So as we start to wind up, Brian, let me just pick up a couple of questions. One is, if you had one piece of advice for aspiring astronomers, what would it be?
I think it's, and it's for aspiring anything, actually, or whatever you aspire to, it's to stay excited about it. If you're excited about something and you're curious, then you will ultimately you'll be able to be good at it. With that other bit of advice that I sort of mentioned earlier, which is don't worry if you find something difficult, because all physicists that I know find things difficult, and it's different things for different people. There are some things that I have to think for 2 months about, and someone else will get it in a minute, and vice versa. And I've met people who we've all had this experience. Same with music, same with art, right? So the thing is that if you want to be an astronomer, you stay excited about it, and you do the work, and you do the practice, and you do your maths and things which you need if you want to do astronomy. And if you find you can't do it, just keep going and understand that it took, you know, as I said, Einstein got things wrong. So Einstein once famously said, this is the last thing I'll say, he was asked a very similar question. I mean, I'm not comparing myself to Einstein, by the way, just no, but he was asked, I think it was at a school, and he said, when I was your age, I was no Einstein, which I think is a great answer.
Yeah, there's a genius in that answer. That's brilliant. So by extension, for NMITE, for the engineers and technologists of tomorrow, stay curious and stay excited about what you're doing, and don't worry. It seems to me you're saying if you don't quite know what you want to be doing, because human beings are evolving and self-discovering beings as much as society is evolving and self-discovering itself. Yeah,
and don't worry if you don't understand something. I think it's really important, because you will find a way of understanding it. It's about perseverance in that case.
Yes, I always think it's a sign of maturity when someone says, look, I'm terribly sorry, I've looked at this for ages and I don't understand. Could you explain it to me?
Yeah.
Okay, now, final question, I think, and it really comes from our president and CEO, Elena at NMITE. She says, Brian, thank you so much for joining us today. NMITE's aiming to educate free thinkers, empowered and liberated to take risks, make mistakes, be able to say, I'm wrong and I've learned from the experience. Future engineers are coming to us programmed not to make mistakes. There's a terrible fear about making mistakes, possibly in the school system or in our wider culture. Is that something that we can do something about? Are there ways you think in which institutions at any level can reprogram them, if that's the right word, or at least open up, give that tolerance, that self-confidence to not to worry about mistakes and to be more open and embracing of themselves and the world?
Yeah, I think it's vitally important. You can look back. I mean, I've given a couple of examples where you can look at people like Richard Feynman, who won a Nobel Prize, who explicitly celebrates not knowing in that process of discovery. I suppose there's one thing which I suppose just unintentionally in the way you phrased it, but it's important to note that as an engineer, it is bad to get things wrong professionally, right? So there is an important thing. If you're designing the ejector seat on a fighter aircraft, for example, it had better work. So I think that's part of the skill of being an engineer. But the process of assuring yourself that as far as anyone can tell, this thing is going to work is, I think, in that process, all the things that we've talked about are necessary. As long as you realize that, don't just busk it with the bridge. Because, just make sure the bridge is going to stand up.
I remember seeing, I think I saw some footage of you at one point chasing the sunset in a Eurofighter, and I'm pleased that the engineers who built that were not busting it.
Although we did have a beta version of the software on it, because it was a research aircraft at BAE Systems, and so he did say there are some glitches in the software, but don't worry.
I think the voiceover where you said we might have to press Control Alt Delete, but should be okay. Yeah. Those planes are not able to fly without software, so they have a natural tendency to fall out of the sky. Look, we could go on, ladies and gentlemen. You'll have seen this for hours. It is an absolute delight to explore these questions with you, Brian. Thank you so much. If I just think about areas we've touched on you playing in the same gig, introducing as Jimmy Page and Led Zepp. You've taken us to the event horizon of black holes. You've compressed the sun into a space of less than 3 kilometers. And it's been the most mind expanding and, if I may say, morally uplifting and exciting event and talk. And I can't thank you enough. I think you've given us a wonderful, not just set of ideas, but an inspiring example of how someone can make their own life on their own terms and in ways that respect their own values. And it couldn't be a better lesson for NMITE and for all of the students that we'll be educating over the next few years. So on behalf of everyone who's on this call and everyone who views it in the future, let me just say thank you so much. We deeply appreciate it, and we're so grateful to you for your kindness.
Thank you very much. I really enjoyed it. Thank you.
Thank you, ladies and gentlemen. Thank you.